Hello and welcome to G5STO's channel. Yeah, this is the Fluke PM6680B fantastic frequency counter, but the 10 megahertz crystal that comes pre-standardized is pretty naff. It drifts all over the place. Well, for the sake of a favour, I've got invested in an oven controlled crystal oscillator, and even that was still a little bit wacky. The last digit here was all over the place. So I embarked on a project to add my own digital to analog conversion and then keep adding the voltage from DAC and see if we can stabilize this thing. Now, it's really hot here today where I live. It's about 35 degrees centigrade. I don't know what that is in Fahrenheit, but it's probably near 100, maybe 100 and something. It's really hot and really humid. It's absolutely terrible. So with the cover on the frequency counter, I can't even imagine what the heat temperature is inside, but I can tell it's really hot, and I'm stuck with my words here. But if we look at this, then we can see, if we just quickly change the gate to let's say 1 second and enter, and we gate at 1 second, we can see that we've got a pretty damn accurate reference here. That's pretty good. That's not hopping around. I've just actually gone up to the computer, and this thing is wireless. It's not wireless to read the frequency. That still has to be done manually, but the calibration is done wirelessly. Fortunately, there's a little hole at the back of this piece of equipment, this instrument, that doesn't require you to drill any nasty holes. You just have to push back a little plastic cover, and then you have access to this hole that was probably some sort of external DC jack or at some point in its life, but never got it fitted. So, and all I've done is fit a Wi-Fi antenna there. So there's some code and some gubbins going on inside this thing. But there we are. Look at that. For just a sort of a £6, £5, whatever it is, oven-controlled crystal oscillator and a DAC and a little bit of code later. And this is what we got. I've got a really accurate 10 megahertz disciplined oscillator. Now, the signal going in, I must say, is from a GPSDO. So I don't believe that's going to move anywhere. That's pretty stable. That's it's 0.0009 off, so it's 9 10,000ths of a hertz off, if I'm reading that right. So that's 9 10,000ths of a hertz off of 10 megahertz. So I don't think this instrument is going to be able to pick up on that. But there we are. That's pretty good. So if we go back to 500, which is half a second, and as we can see, it's super duper stable. It's stabilized now. The temperature's got up to temperature, and the internal temperature of the instrument is now stabilized. Just the odd little waver, but we can put that down to, it could be from anything from noise or jitter or whatever. But look at that. That's brilliant, isn't it? And in the second part of the video, I'm going to discuss the web interface and also some of the... Welcome back. Oops. Hello and welcome back. For the second part of this video, as we can see, this is the Wi-Fi signal coming from my local network. So that's the oven-controlled crystal oscillator via a WeMOS D1 Pro Mini connected. We've got our RSSI, SSID here, RSSI, and I haven't got it fitted at the minute because I haven't got one on hand, but I've ordered one. But we're going to put basically a thermistor on the crystal on the oven. We're going to keep an eye on the temperature all the time. But what we have got here is a DAC. Introduce the DAC into the chain of the crystallized oven. The oven crystal. So we've introduced a DAC, so we can add a tiny weeny bit of voltage, so we can adjust the offset and make it really accurate. Now in the code, there's some really good averaging code going on. So that means that basically it learns from the temperature, it learns from everything, adds it all together and says, hey, this is the reason why it's going off. Now we can trim that, or we can do this and we can do that. So we know that on startup, at the moment obviously we haven't got this, so this part of the code is null and void. But later on I would literally add that into the code. So that means that when the temperature goes up, we'll know how to trim just a little bit. Obviously this thing is going to be null, it's going to be dumb. It isn't going to know what the frequency is. That takes a lot more grief than what it's worth for just a simple instrument. But what it basically will do is it will remember the code and plant it in the EEPROM, so we'll have a really good idea of what we're expecting in the way of coarse and fine trim at certain temperatures and certain frequencies and so on. So going on first startup, obviously we're going to get a really big swing from high to low, and then it'll start averaging out. But what we do is we can slide this slider up and down, or we can just simply add just a few millivolts here, and that will go up fine and coarse, and we can obviously keep an eye. At the moment it's on 10 megahertz, so 10.0001002. So we're going to add a little bit of voltage. Obviously you can't see that. I'm going to add just a fraction more to compensate. Now we're back onto 10. So it's fluctuating just between 9, loads of nines, and then 10. And now it's stabilised on 10. So that's really accurate on 10. It's not moving from 10 at all. And that's our adjustment. So we've added 0.422 to the chain. Add more voltage, and it brings the frequency down. Reduce the voltage, and it sends the frequency up. So it works, I suppose, like if you like, in a clamping fashion. The voltage clamps the frequency. So yeah, that's it in a nutshell. The value here is just that's the raw value. It's clamped off at 4 volts. Really, I should really clamp that off a bit lower, because it's still using a LT1009 voltage reference, and then it's just adding the voltage to the voltage reference in very small increments. So there's no point in trying to this is only still at the end of the day a £5 crystal oscillator, and it's hardly worth the aggravation to sort of start reinventing the wheel on that. It's always going to be a £5 crystal oscillator, but we can improve it, and that's exactly what we've done here by simply taking this reference voltage and adjusting that reference voltage. We can then basically take away all the ambiguity. It's still sitting there at 10.0000000. 1, 2, 3, 4, 5, I think it's 9 zeros, I'm not sure. 1, 2, 3, 4, 5, 6, 7, 8 zeros. 10 point and then 8 zeros. So that's this 10-digit counter. So yeah, so there we are. Fantastic. 73. And for the final part of this video, I'm going to give a quick demonstration. As we can see, the calibration frequency is well off. We've got the GPSDO coming in here. That's a really steady 10 megahertz signal. And then we're going to go up to here. We're going to move the mouse over to the trim. I'm going to watch the frequency change as we trim the frequency. So here we go. Bring it down. Whoops. Laptop's moving on me. Let's bring it down to about 400 millivolts. 407 millivolts. There you go. It's nearly on there. So you can see the frequency's changed. Now we need a little trimming there. So as I say, if you listen to the first part of the videos, then you know that this works on a clamping idea. So if we look, frequency, time up time, got the temperature, which is a work in motion, got our signal here, calibration tables. At the moment there's no calibration set because there's no thermistor connected. But if we go here and we check our frequency, we're going to go up in an increment. So we're going to 408, and it comes down a bit. 409, maybe we need to go up by 10. That's 421. 421, we're nearly there. 422, 24, 25, 26, maybe 27. There you go. So we've got here 0.427, and there we are, spot on calibrated. So yeah, so you never have to really flip the lid on one of these things ever again, and that is absolutely rock solid 10 megahertz, as sharp as the GPS though. This has not been on for very long. It's only been on for like 2 or 3 minutes, but already the temperature's up because this has got the standby. So when we turn this off, the power to the to the oven controlled crystal oscillator is constant. It's always on so long as this equipment's plugged in. So when we turn back on again, we should get an immediate 10 megahertz on the nose, which we do. So that's brilliant. So if we quickly go into time, we change the time to say 5 seconds. 5 seconds, that's pretty good. Enter. And let's have a look at the averaging over to 5 seconds. And there we are, which is pretty good. That's pretty good. I don't think you're going to get much more stable than that. I'm trying to get both in focus together. It's really hard to sort of get that in focus whilst keeping that in focus. So I can zoom out a little bit. So I've got this on the workbench in a minute. It's a bit tight. There we go. It's not moved there from 10, which is pretty sharp. That's pretty good. I'm happy with that. And as I say, this is our calibration data here, and we are at 0.427 volts. Not sure what that extra V is. Maybe it's a typo. I might have put a typo something. But then obviously, if this temperature was here, if this was functioning, then I would hit this button here and say save calibration temperature. So we next know that when the thermistor is at this temperature, the program will automatically trim. So if, in fact, it's working actually like a temperature compensated crystal oven. It's like a sort of, it's automatically compensating with time and with temperature, and it also trim. So there we go. So, but obviously I'll just hit this button, save calibration temperature, current temperature, and that would log it to this map here. No calibration point to save for this bank. And if I go up, there's actually 3 banks that we can refer to. So hold a second. So down, and then we have a calibration plot as well. So there we are. I think I might have, oh there we are, sorry, I've moved it around a little bit. And then if we click on bank 1, we have 3 different banks of calibration data for whatever reason. Say if we want to use some sort of external reference or whatever and we can still show that there's a, there might be calibration between a certain temperature from switch on, from warmed up after 10 minutes and warmed up for 20 minutes. We can just simply change our banks around. So that's in a nutshell. And as I say, we've still got a Wi-Fi signal, 60 dBm. And if, I'm not going to hit if I hit the calibration mark now, like this, save calibration data, we immediately get that popped in there. So it tells us about 350. But we've got some sort of crazy infinite temperature there. So the thing's going to get confused, which is likely. And we've got our first calibration point on there. So whoops, so I'll quickly go up a bit. Now the good news is, now what if I do something here? So if I hit 10 on the calibration, right, so I'm going to go up to 440, which sends this down in frequency. Yeah, but this learns. It learns that we've changed frequency, and eventually it will compensate and come back up, and there we go. So it's gone back up to 10 megahertz because it knows what the trim frequency is at that temperature. So no matter what I do to this trim now, because I've locked that temperature at that particular point, at that particular voltage, we're always going to get back to 10 megahertz, which is really quite clever, isn't it? So, even though we've changed the trim voltage, so we change the trim voltage again, because the temperature hasn't changed, see, we're way off all of a sudden, and it says, hang on a second, we're still on the, if we change the time base actually to, say, let's go 500 milli, enter, and then we're back again. So if I change it even more, let's go the other way now, let's go really low, let's go something like, what are we at, 3.91, so that's well off, 19, 20, hello, you've made a mistake, it says, and it's brought me back to 10 megahertz again. So it's smart enough already to work out that we're all over the place. But the thing is because it's temperature compensated now, it understands that if the temperature changes, then it's going to throttle and change the this here. But if I remove the calibration data, see, if we go here and I go reset calibration map, okay, are you sure you want to clear calibration? Which is yeah. Let's do that. The calibration's off, and in a second now this will change because we know we're well off. So let's quickly hit a 1 or something. There we go, well off. All over the place. And that's not going to correct itself because I've just deleted the calibration table. So that's just going to sit there well off for the time being because I've actually deleted the calibration table. And that is not going to sort itself out. But if I add a couple of ones, I'll go back to what we were saying, 4.07 I think it was. 0.08, nearly there. It's got about 10, maybe 420, nearly there. Maybe another 10, 432, might be a bit high that. Let's go down by a couple, 430, which is about right for this temperature. Yeah, it's okay. Let's go right. Let's go 431. Maybe too much. Let's go the opposite direction. 429, 27. 429, or whatever we stand there. 429. Then we're back on spot on. So the oven hasn't actually warmed up properly yet, so we're going to get a bit of jitter there. But as soon as the oven sort of settles itself down, it's only been up for like 8 minutes now. I'd expect that to be a little bit more stable after sort of maybe 20, 25 minutes. There we are. So it's pretty good. We're working well. And it learns. So in essence, once the program's actually running and the temperature's actually noted, we'll never really need to even dive into the program at all in the future because it'll just simply keep the calibration and the frequency and everything all tuned to each other. There we go, 73s.